Alright guys, welcome back to one last problem solving section. Last minute, sorry about that. But we're just going to try to be pretty quick and crush through this homework here. So this one we're going to try to find our shear and bending moment diagrams. We've got two forces called P, each a distance A from their respective supports, and a total distance of L on the bottom. Now it's pretty easy to tell that with these 2-point forces called P that are vertical, you're going to have 2-point forces called P that are going to be your support reactions. But let's go ahead and do the summing so that we can get used to our used to the way that we're doing these L's and A's and L's minus A's and whatnot. So we'll just call this A and point B, big A and big B. So if we sum our moment about big A, we're going to get that we have this P, distance A, that's turning it clockwise. So we have minus P times A, and then another negative minus P times, this is a distance of L minus A, L minus A, and then we're adding plus BY, I guess, BY times L. All that's going to equal 0. What we get is that B equals P, BY equals P. Alright, so that down there is P. And then, if you sum, I'll just write it real quick, Fy equals 0. You get 2P minus AY, or whatever you want to say. Anyway, AY is also P. Alright. Beautifully. P. Alright. There's our free body diagram. This is distance A, this is distance A, this is distance L. And as you can see, because of this point force here, this point force here, these guys, we're going to need to divide this up into 1, 2, 3 sections. Alright, and as you can also see, with these point forces in the middle pushing down, it's going to be concave up, smiling. So you know that the moment diagram is going to be, so let me just draw the shear diagram. You don't have to draw these axes before you do your calculations, but we just know that moment's going to be all positive, and you can tell that shear is going to have some negative components too. But anyway, let's go figure that out. Alright, so for 0 is less than or equal to x, which is less than L. Sorry, which is less than A. Alright, and the reason that we say less than A is because we're not supposed to analyze directly at the point force P, so we're going to have to be just a little bit to the left of it. We make the exception with those support reactions. Alright, and so what we have is this section starting from the left with P here, and then we have our shear and our bending moment that are both drawn in the positive conventions that we're just always going to draw them that way, and if it turns out that we need to flip them the other way, then we're just going to be negative on our diagrams over here, right? So if Fy is going to equal 0, then what we get is P minus V equals 0. Alright, easy enough. V is equal to P. Great. And so, actually, let's just go ahead and bring this down. Alright, so this is distance A, this is distance L minus A, and then this is L down here. Alright. So V is equal to P up until A. That's P. Alright, now if we do our moment. Okay, so the moment's a little more interesting because, this is our X is going this way. In each increment of X, P is creating a bigger moment. Every time you move, this is P times not very much, this is P times more. And so we have this, moreover, if we're pinning it everywhere I'm putting my pencil, it's always going to be this clockwise rotation. So we're going to call that minus p times x, okay, plus m equals 0. All right, so m equals px. All right, so then it's going to just be a straight line. This value is going to be pa. Cool. All right. Now if we go from a is less than x is less than L minus a, okay, then we can do draw our section out, so it's going to look something like this, where we have a P and another P, distance A. Alright, and then we have, per usual, our V and our M. Okay? Summing Fy, we see P minus V equals 0. So V equals 0. Not bad. Alright. M. We have px from last time, the minus px. And then once we get to A, to distance A, now this point force starts to make an impact, and as we go further from there, it's pushing the bar counterclockwise. And so that one's going to be plus p times x minus a, because it only starts to count once we're a distance a in, okay? Plus our m going to equal 0, and we figure that out. We got that cancels with that. We've just got a PA and an M. We get M equals PA. And now PX down here, right, that was our varying, but A is just a constant. A is just a constant distance, and we actually got up to the value of PA with that first one, right? I mean, as we'd expect. So this is just going to be a constant. Alright, just one more section now. We've got L minus A is less than X is less than L. Okay, and I kind of like the way they do it in the solutions that are posted. It's a good way to practice kind of your conventions, your positive conventions on the other side. So remember that this is what we're doing right now is method of sections, right? So you can cut it however you want, as long as you account for all the forces that you have to account for. So we're gonna go from we're going to put our reactions on this side. So we're going to have V, our positive V is going up now because it's going to be turning our section clockwise. And then our positive M is still trying to make it smile. Okay? And so now, if we sum in Y, we get V plus P equals 0. So then we know that V equals minus P. Okay? So now P minus P. We were 0 throughout this. Now we're down here. These are not well proportioned, but this should be the same as that. Alright, finally. That's an M. We have, so now that we have, so this, bear in mind this is still our positive M, okay? This is our positive convention for M, but much in the same way that over here in our summations we treated V as a negative, in the summations, v was negative because it's pointing down. We're going to do the same thing with this m because it's turning our section clockwise as x progresses along, which is negative because I should be drawing these, but you know, we have the counterclockwise convention, right? So we're going to have minus m plus p times L minus x? Yeah, because this distance L minus x is going to be how much that's contributing. Equals 0. And what we get is m equals p times L minus x. All right, which you can verify this yourself, but ends up looking just like that. All right, and that's the problem. I think this, well, the second part has you plug in variables, but I think you can do that. But this is a really good one to check your bearings on and be like, you know, sure that you kind of get the process, and then you move on to the distributed loads, as we will do. All right, problem 755, we have a 40 kilonewton per meter distributed load. That'll be fun. All right, so real quick, let's do our support reactions. So 40 kilonewton meters over 8 meters, it's 300, it's basically 320. All right, I'm not actually going to write it as 320. All right, so we know this is an equivalent load of 320 because it's 40 over 8, but I'm going to go ahead and write this as 40x right here, okay? We're just going to do this point load so that we can do our moment summations for finding our AX and our AY and our BY. Okay, we've got 150 over here, and we have 20 here. Okay, so support reactions. We've got our moments. Let's sum moment about B. This is point B here. So summing our moments about B, we get 40 times 8 is 320 applied 4 away. So, well, I'll just write that as this is turning it counterclockwise. Alright, so 40 times 8 times 4. Okay. Minus 20 times 3. Okay, minus 150. Plus AY times 8. Okay, all equals 0. We end up with AY equals to 133.75. Same if you do your FY's summation, then you'll get that BY is going to be 206.25. And these are kilonewtons. I'm being lazy with units. Alright, so this is 133.75 and 206.25. Alright, so we only need to divide this into two sections because this distributed load is over the whole thing. We don't actually need to break it up where we've done this little point load. This is where you don't want to confuse yourself with point loads because that we still need to treat that as the distributed load that it is. Anyway, so from 0 is less than or equal to x, which is less than 8 meters. That'll get us to point B. I'm going to go ahead and draw what we have, okay, with a little more room than that. Alright, so we've got our 133.75. We have 40x, a distance of x over 2. So saying that this whole, whatever our whole length is going to be x, then we're having our 40x equivalently applied x over 2 away. That'll come into play for the moment. Anyway, then we also have our v and m like we do. And so for summing in y, we're going to get 133.75 minus 40x minus v equal to 0, and so we get that v equals 133.75 minus 40x. Okay, cool. Now summing in moment. I always do that. I'm expecting to go to fx from all the different truss work we've done. Okay, so now we have our 40x, that's a distance of x over 2, right? And that's going to be turning things counterclockwise. Actually, first let's do our little point force. I like to work across. So we've got 133.75 times x. This is going to be minus because it's tending to turn it clockwise. X, okay, and then plus 40x times x over 2. And plus m is going to equal 0, and so what we get is that m equals 133.75 x minus 20x squared. Okay. We'll go ahead and draw that in a second, but just notice now that 20x squared is the integral of 40x, the indefinite integral. 40x integrates to 20x squared. Then this 133.75x helps make it definite. So I'm not going to draw this all perfect and whatnot, but you know, this does something like that, and this does something like that. Okay. Next, we have 8 meters is less than x, which is less than or equal to 11 meters. Okay, and this one we're going to do the thing we did last time where we go from the other end. Okay, so we're going to have our M here and our shear. Okay, and then we've got our 150 and our 20. Is that everything? I think that's everything. Alright, so let's sum in our y direction. That's not too tough. We've got v minus 20 equals 0. So v equals 20. Neat. And then we have in m, we have our positive convention m, right, is going to be negative right now. So minus m. Yeah, so minus m minus 20 times whatever. Okay, so minus m minus 20 times, that's going to be the full length, 11, minus your x. And then minus 150 equals 0. Alright, and that eventually works out to m equals 220x minus 370. Okay, and I'm just going to go ahead and complete the graphs by kind of looking at the answer key, but we can talk through them here in a second. Alright, and then this one sort of goes like that. Alright, so what we see here, let's talk through it. Let's talk through it a little bit intuitively or whatever. All right, so this is what you end up with when you have a uniform distributed load, right? You have this shearing that it starts out at this full positive shear, trying to turn it clockwise, and then it's trying to turn it kind of less and less and less clockwise until you get to halfway between the two supports. This is for when you're supported on either end of a uniform load. And then you start getting this negative part whenever this starts trying to turn things counterclockwise. So it's just this nice continuous gradation from there, okay? And then you have this jump up, right? And the magnitude of this jump here is the same as this 206.25. And then from there on, you just have this shear of 20. This magnitude right here is 20. So you see that these like point forces kind of, this distributed load change the shear continuously, whereas the point forces, it just jumps at that magnitude. Jumps up to a 6.25 for that, jumps down 20 for the end. All right, now down into the bending moment. This is going to be quadratic, okay? And you see that at some point, so like these forces over here are bending on this over this way, right? And whereas this force here is pushing it down, and they're sort of bending it around B. And so what's cool about doing these kinds of diagrams is you see that this zero crossing, right? Wherever the forces from this side and the forces from that side cancel out, it's actually a little bit over to the left of B. And this is the kind of thing that's really important when you're designing, mechanical components. Also down here, I kind of want to point out that you can see sort of this stacking of the 20x, and then of this, just like this part down here is due to the 150, whereas this part up here is due to that 20 kilonewtons times the x. And so you see they just kind of they sort of stack up on each other. All right, problem 7.77-77, we've got these two different bending moments that are applied at the ends of this beam, and we've got this one uniform load in the middle. All right, I went ahead and drew the free body diagram with the support reactions figured out. If you can't do support reactions at this point, go practice them. I've got a lot of older videos where you can see that, but I just kind of wanted to talk through this one and not necessarily do it so formally like we did the past few. Just kind of do it sort of quick and dirty. So let's take a look at what we've got going on here. Notice how I drew this to remind myself. I mean, I copied this from the book, but you can remind yourself that this is a distributed load even though you're drawing this thing while you're making your free body diagrams. This is a 2x, right? All right, so if we're going to look at our shear diagram, starting from over here, there's no shear, right? Because this bending moment, these are idealized pure bending, okay? And so we don't have any shear introduced until we get to this 20 kip. So we're just going to go ahead and follow that 0, and then at the 20, we're going to jump up 20, because that's what we do when we hit these things. So that's a value of 20 right here. Okay, not gonna move on yet. So then this 50 that's pure bending is basically the same way that we would treat, kind of the same way that we treat these two, this sort of pure shear, right? So this 50 that's bending it like a frowny face, the negative way, means that we're gonna come down here to minus 50, and then all the way up to that 10. You're just going to have that constant bending moment. All right. So then we have our distributed distributed uniform load that's 2x going down, and so that's basically minus 2x on our graph. So from 10 to 30, that's 20. 2x over 20 means it'll go down 40. So we'll end up at minus 20. Call that minus 20. This is positive 20. All right, and so that's just going to go straight down to there. This 0 crossing is right in the middle. It's right at 20 feet along the bar. Okay. Shade it so we see where we're at. All right, so now if we want to look at our moment, we know that since this is going to be this linear function, we know that this guy is going to be a quadratic. What more is that we know this is a negative linear function, so we know this is going to be a concave down quadratic. All right. Now, if we do want the exact numbers, well, let's go ahead and figure out what's going on here and then integrate it to find out what's going on here, right? So here we have just between these two sections, right? We have v equals 20 minus 2x, right? We've got our 20 kilopascals, not kilopascals, 20 kips minus our 2x as we go along it, right? And remembering our relationships that we talked about, where m is the, or change in m, whatever, is the integral of v dx. Well, let's integrate that 20 minus 2x, and we get 20x minus x squared plus c, right? And, well, what is our plus c going to be? We don't have any, sorry, we know that our constant is going to be this constant that we've put at the end of the bar. So that's going to be 20x minus x squared minus 50, okay? And that ends up looking like that. Yep. Ooh, where this top bit ends up at 50, at plus 50. All right, and then the other side of the equation, again, we have no shear, right? Because these guys have all taken care of each other, and then this is just this hanging bar and pure bending of negative 50 again, because it's putting it concave down. And that gets us our whole thing. Now, I know that seems a little like a little hand wavy, probably because of the waving of the hands that I did. But if you did want to look at this middle section, right? Where we've got our 20 kip, and then we've got our 2x distributed load here, and then there was this 50 KIP, right? If we sum in our y, we get 20 minus 2x minus v equals 0, which gets us our v equals 20 minus 2x, okay? And if we, am I off the edge? Yeah, I'm off the edge, all right. And if we sum our moments, we have that, that constant minus 50. All right, so if we're summing it, sorry, I should have put this here. That's our V, that's our M. Okay, so as we're going down this way, that 50, even though that's a negative bending moment, it's going to be pushing things counterclockwise, so we can say minus 50, okay? And then, I'm sorry, plus 50, that's my bad. That's a plus 50, all right? And then we have our 20, that's pushing things clockwise, okay? Yeah, clockwise. Sorry. Okay, so minus 20 times x as you're going along. Okay? And then plus this 2x being applied at a distance of x over 2 from the moment. plus m equals 0. And then you get m equals 20x minus x squared minus 50. Okay, so you can see that, you know, you get the same thing here and here. This way you just did a little bit of sleuthing to eke out that constant instead of just breaking into sections and working through. You can see from inspection really what that constant is going to be, that minus 50, and you can use the integration just to make your life a little bit easier, or as a double check, you know, sanity check. Any of those ways are going to be totally fine on the test.